In this lecture, we will be talking about Newton's second law in rotation. Torque equal to I alpha, or in other words, external torque is directly proportional to the rate of change of angular momentum. So, generally we apply this equation about 2 points, specifically about these 2 points. One is center of mass, another is axis of rotation, the point about which body rotates, or a stationary point on a rotating body. So before moving to application of Newton's second law, we must know what torque is and how it is calculated. So torque is always calculated about a point or about an axis. In this lecture, we'll be talking about torque about a point only. So torque about a point is r cross f, where r is the position vector or position of the point of application of force from O. This is quite important to note that what is r. We can also write down the magnitude of torque as rf sin theta in this diagram. Rf sin theta, where theta is the angle between r vector and f vector, which can be turned into r perpendicular f. R perpendicular is the component of r which is perpendicular to the f, or component of position vector perpendicular to the force. R must be calculated or measured from point O, about which you are about to find the torque. This is an important example in which we will discuss the equilibrium. There are two blocks and their distance from the axis of rotation, or about the point about which the whole system rotates, are R1 and R2 as shown in the figure. For equilibrium, torque about O should be 0, and in fact, if the body is in equilibrium, torque about any other point will be 0. So m1g is the force and the perpendicular distance from O is R1, minus m2g R2. These two torques are in opposite directions, so we took one as positive and another as negative. These are the two main torques. There will be another force of the hinge, but if we take its torque about point O, it will be 0. So m1 r1 is equal to m2 r2 after cancelling g. Another very important example in which a massive pulley is being rotated with the help of these two masses, m1 and m2. Constraint says that the acceleration of these two masses will be equal, let's say a, but the tension in both sides of the string will be different, because we have to rotate a massive pulley, and to rotate that we require a torque, and if these forces are equal, they will not be able to produce a net torque about its center. So the forces are different, and if the pulley have this anti-clockwise alpha, obviously T1 is winning, so T1 will produce more torque than T2. So first of all, we write down the linear equations, or LOM, laws of motion equation, in linear forms. And this is the torque equation. T1r minus T2r is equal to I alpha, and I about the center or about the axis of rotation, which is same in this case. A equal to R alpha, as there is no slipping. So from these four equations we can find out T1, T2, A and alpha. The next example is also very important, in which a spool with inner radius as r, small r, and outermost radius as capital R is tied with a block and released from rest. So let the acceleration of the center of the spool is a, and it rotates with an angular acceleration alpha. So if we'll talk about this point, see the cursor, the acceleration of this point will be a because of the center, plus capital R alpha in the downward direction, and acceleration of this point, see the cursor again, this point will be a minus small r alpha, and as the string is at rest, so acceleration a minus small r alpha must be equal to 0. So we got a equal to small r alpha from this point, and acceleration of the block as a plus r alpha. These are two important relations, must be considered, and without them we will not be able to solve it. Then again, writing the torque equation. At this moment, if we'll take torque about the center, the torque of T1 and T2 adds together. They try to rotate the spool in same clockwise direction. So we'll add these two torques, T2 into small r plus T1 into capital R equal to ICM alpha, and simple these linear equations of forces and acceleration. This is for spool, equation number 2, and equation number 3 is for the block. And with the help of these four equations, we can solve for T1, T2, alpha and A, as well as acceleration of the block. This example is an important result, must be remembered. So what's the case is, you have to find a height edge above the center where the force or an impulse is applied so that there's no slipping takes place, instantly it start pure rolling, or we can say that the friction will not act, or even if the floor is smooth, it will act. Oh, it will start pure rolling. Okay, all the three statements which I gave are same. So let it to be height h above the center. So what we did, we applied our torque equation about center, and as it is pure rolling without slipping, we put A equal to R alpha. So this is torque, this is ICM, and A by R is the value of alpha. From this equation we get H is equal to K square by R. It depends on the geometry. For example, if it's a ring, H will come out to be R. If it's a disk, H will come out to be R by 2. And if it's a solid sphere, it will be 2 by 5. So for different bodies, the point will be different. It's an important result, keep it in mind. Another important observation we can take, if the force is applied above this point, then acceleration will try to remain same, and alpha will increase according to this equation because the torque will increase. So the bottommost point, which has an acceleration A in forward direction and R alpha in backward direction because of rotation, will now try to move in backward direction as alpha increases. So if friction is available here, it will act in forward direction if F is applied above this point, and if F is applied below this point, the reverse explanation can be made and the friction will act in reverse direction. So what's the observation is, F is applied above that point, friction is in the same direction as of F applied, and if F is applied below this point, then friction will be in opposite direction, which will act on the disk or the object. This example is also a important result, must be remembered. So you have to find a minimum mu, so that if an object is released on an incline having an inclination of theta, it must pure roll. So again, as the case is limiting, we will put friction as mu n in the final equations. Mg sin theta minus friction is equal to ma in this direction, and torque about Cm will be Fr friction into R ICM alpha, and again, as there is no slipping on a fixed ground, ACM will be equal to R alpha. From these two equations we can get the value of A, which is independent of mu or friction. In case of pure rolling, the acceleration will be this, no matter what is the value of friction or coefficient of friction is, and the friction acting will be this. So if we put friction as mu n and n is equal to mg cos theta, the minimum mu will come out to be like this. So remember the acceleration and minimum mu, or just few observations, because in this, especially in this problem, they don't ask you for the value of acceleration of minimum mu. They ask you just these questions, which I jot down below this. So let's take an observation in our mind, that if k square by r square is more, if k square by r square is more, then A will be less, okay, and the time taken to reach the ground will be more. As A is less, friction will be more, and in fact that is the reason, because friction is more, A will be less. Okay, so if k square by r square is more, friction will be more, A will be less, time to reach the ground will be more. So just remember this, that uh, disk has the maximum value of k square by r square, which is 1, and then we follow hollow sphere, which is 2 by, oh sorry, I just pronounced it wrongly. Ring is having the maximum value of k square by r square, which is 1, then which is followed by hollow sphere, which is 2 by 3, and then disk, and then solid sphere. Okay, so time to reach the bottom, again acceleration is least, so solid ring will take the maximum time. Speed at the bottom, as all are moving the same distance and acceleration of the ring is minimum, so its speed at the bottom will be minimum. Just listen these explanations very carefully and do write them, otherwise you will not be able to understand what I'm saying. Omega at the bottom, as all are performing pure rolling, so whoever has the minimum speed at the bottom will have minimum omega at the bottom, which is disk, sorry, ring. Friction force in case of no slipping. Uh, Again I told you that more the acceleration, less will be the friction. So ring has minimum acceleration, that's why having maximum friction. Tendency to slip. Tendency to slip is maximum in case of ring, because it requires maximum friction. Total kinetic energy of the bottom, as there is no slipping taking place, static friction acts and it perform no work, no loss of energy, all will have same total kinetic energy at the bottom. Omega at the bottom, if particle rolling and slipping takes place. Oh, if partial rolling and slipping takes place, it's a very important question. If partial rolling and slipping takes place, as it is slipping, the force of friction will be same, mu mg cos theta in all the cases, and torque about cm will also be same, which is mu mg cos theta into r. So whichever have the least moment of inertia will produce maximum angular acceleration and will have maximum angular velocity, which is solid sphere. HS means hollow sphere, R means ring, and D means disk. The last example is a rod is standing at an angle theta with a wall and it's just about to slip. So and in fact it's slipping, let's assume it is slipping, so we have to find its angular acceleration. So what I did, I shown the forces n2 from the wall, mu n2 in upward direction as this point is slipping downward, n1 in upward direction, and this point is slipping in forward direction, so friction on it will act in backward direction. So just look at the diagram very carefully. If I have to take the torque of friction 2, then what I did, I found out the perpendicular distance of, just draw this line and try to find out the perpendicular distance from the point about which you are taking the torque, which is center of mass of the rod, which is equal to L by 2 cos theta. So friction into arm length or perpendicular length is this. Similarly, n2 into its perpendicular distance, which is L2 sin theta. These two torques are in the same direction about center. Friction 1 has the same direction torque, but n1 has opposite direction torque. So these two torques will add, and subtracting these torque, we get the net torque about center of mass or center of the rod, ICM alpha, and equating these values we can get the value of alpha. We can also write down the equations in linear equations. N2 must be equal to friction 1, these two vertical forces will balance mg, and so on. Okay, so remember everything what I told you. Thank you.